Yeah, welcome everybody to our SPCLB cast and in the bi-weekly cadence. So today I'm very glad that Michael Bauer is going to tell us about Legate and Legion, and Nikolai will give an introduction of him now.
Okay, thank you, Torsten, and thank you, Mike, for agreeing to come in and give a talk. So Michael Bauer is a principal research scientist at NVIDIA Research, where he works on making it easier to program large clusters of GPUs. He is the primary author of the Legion runtime and also works on this new Legate system that he's going to talk about. He's published numerous papers, especially in conferences like supercomputing, that are especially relevant to our general audience. And with that, I'll let Mike tell us more about Legion and Legate. Thank you.
Sure. Great. Thanks, Nikolai. So I'm going to be talking today about sort of our approach to doing what we call high productivity, high performance computing with both Legion and Legate, and I'll explain what each of those systems are throughout this talk. I'll say at the beginning, if people want to ask questions, please just write them in the chat for Nikolai, and you can interrupt me and stuff. I definitely want to take questions. In the middle, I'd rather I have way more material that I can get through in an hour. So if you guys have directions you want to learn about or go into more detail, please just let me know. Okay, so first, I want to provide a vision of what we would define as HPHPC if we could actually do it today, because I think it's valuable to sort of describe what our goal is with doing high productivity, high performance computing. And the place that I like to start here is in the Python ecosystem, because Python is actually a really great language for doing productivity and development of codes and really trying to just get a feel for how you're going to set up an application and all the different components of it. So imagine, for example, like we want to do like a large direct numerical simulation of some combustion chemistry example with multiphysics and stuff. Well, I might start off in Python writing that in NumPy. Right, so I can have like multi-dimensional arrays that represent, my spatial dimensions and chemical species and stuff, right? And I can write nice, very, very simple syntax to iterate over those cells and do all sorts of math and stuff with them to actually run that simulation, right? And if I want to do some analysis, I can pipe some of that data over to Pandas. I can just pass those NumPy arrays straight into Pandas, right? Do things like statistical analyses, trying to look for patterns in my simulation. I can also pass data back from my analyses for doing things like uncertainty quantification. So I can get columns out of my Pandas data frames, pass those back into NumPy. All those things just kind of work together, right? I can pass data into matplotlib to make plots of what's going on in my simulation. I might pass some data into scikit-learn or to do some SPI classifiers to recognize flame wavefronts in my simulation. Pass that into VTK to do some visualization, and pass data back and forth between Pandas and my visualizer and so forth for all those different things. Right, and so this is sort of my ideal ecosystem. If I could build HPC applications, I would like to just write code like this and prototype it like that, and then just have that run at scale on supercomputers. But of course, I want to call out before I talk about why that doesn't work today. Let me just call out a couple of important things about this ecosystem that you set up. One is that there's dynamic typing here with late binding, which really allows you to prototype very easily. You can just pass objects between libraries without having to worry about their data representation. Things just kind of work, right? I have a global namespace where all my objects appear to live in the same namespace, and I can just pass them around. I don't have to worry about partitioning or data management of how my data is distributed or whether it's on the CPU or GPU. Right, and finally, I get sequential semantics. Right, this looks like a single-threaded code. And any parallelism that exists behind the scenes, whether it's in NumPy or scikit-learn or BTK via calling out to OpenMP or graphics like OpenGL is all kind of implicit. I don't have to think about that when I'm writing my Python level code. But of course, this doesn't actually work at scale today, right? If I try to run code like this on the Summit supercomputer, right, things kind of fall apart, right? And the reason they fall apart is you have to worry about distributed memory and CPUs and GPUs and all those kinds of things. So let's just break down why it falls apart because it's going to be instructive for how we're going to move forward. Right, so probably the first thing I have to do is use a library like MPI for Pi to help distribute my computation, right? And the first thing that's going to happen, I have to run different parts of this computation on different numbers of nodes, right? I'm probably going to run my simulation on n nodes, right? Then maybe my statistical analyses run on m nodes, whereas my visualization, is going to run on one node, so I can hook up an X server to it, right? And that sort of destroys a lot of these different properties, right? I've got to write data out to to files, to do file IO, to pass data between, running on n nodes and m nodes. That destroys my ability to pass data back and forth between these different phases of my computation. I become IO bound. I can't pass things I'm not limited. I'm not keeping things in memory. I have to manage explicit Go cells when I'm writing my NumPy code now for exchanging data, right? If I try to use CuPy for running on GPUs, I have to make an unfortunate choice of like running on one process per node where I can get advantage of NVLink, but I can't use like drop-in CuPy because drop-in CuPy for NumPy only works on a single GPU. Or I could run one process per GPU and then I can do the drop-in CuPy, but I can't use GPU direct between the GPUs. So, or sorry, use NVLink between the GPUs because there's no GPU direct for that. So this sort of like, you know, this ecosystem, this great HPC or HPHPC ecosystem kind of falls apart when you have to take into account performance considerations for the kinds of machines that we really want to run real workloads on. And that's problematic. And so what I want to talk about today is how we can actually, you know, design a system or design two systems, Legion and Legate, which, you know, are designed to help us get back to that sort of ideal HPHPC ecosystem and make it possible to run that class of program on a supercomputer without any changes to that original source code. So really the crux of why I think, you know, that we really suffer this problem is like, if you look at like a library developer who maintains something like NumPy or Pandas or any number of HPC or HPDA, HPDA is high performance data analytics libraries, right? Like they're really getting squeezed on all sides from various different directions, right? They have to deal with a complex library API that they're responsible for implementing. They have to deal with lots of complex hardware targets, everything from like single GPU to multi-GPU within a node to like, you know, machines with many GPUs like a DGX superpod or some supercomputer. And they've also got to deal with all those complex interactions with other libraries like NumPy and BTK and stuff, right? So they're really suffering pressure on all sides, right? Those library developers are really at the crux of this problem. And so one of the things that we want to do in the Legate and Legion ecosystems is really try and alleviate some of these pressures that these library developers are feeling, right? So we want to sort of help isolate them from some of the complexities that they have to deal with interacting with other libraries, and also do something about, you know, the complexity of dealing with lots of different kinds of hardware and making it possible to write code that's, you know, more easily portable to lots of different styles of machines and different scales of machines. Okay, so the solution that we're going to take is really based on a very old idea, and we're just going to apply it in a new context to try and address this problem. You know, ever since like the 80s and 90s, all the way through the early 2000s, right? We sort of lived in this sort of wonderful world where we had these great hardware out-of-order processors that had, you know, a nice sequential instruction set architecture where you just have like a stream of instructions with the registers they're accessing. And, you know, we could build all sorts of awesome software on top of that was all single threaded, right? People built awesome libraries. Some people wrote programs directly to the ISA. Some people built on low-level libraries. Some people built on giant towering stacks of libraries, right? And no matter what, this hardware out-of-order processor would sort of like take your stream of instructions, find instruction level parallelism in there, and, you know, make it magically go fast, right? And of course, that all fell apart when we have, you know, thermal scaling limits and stuff like that. But the idea that we want to take here is effectively to do the same thing, but at a coarser granularity, right? We effectively are going to recognize that, you know, this Summit supercomputer actually shares a lot of things in common with the architecture of, you know, that single threaded processor, just at a much coarser granularity. Right, like you effectively have, you know, queues for running things on CPUs. You have latency queues for things on running on CPUs, latency queues for running on GPUs, data movement queues for moving things through NICs. Right, you've got, you know, system frame buffer memories that are effectively, you know, very NUMA-ish in their sense that they're, you know, non-uniform to access, sort of like banked register files. Right, there's a lot of similarities there with how, if you squint at that supercomputer, it looks very similar to that sort of out-of-order processor, just at a much bigger granularity. And so what we want to do is define, you know, sequential execution API on top of this supercomputer and have an implementation of what we're going to call a software out-of-order processor. It's going to provide a lot of the same implementation, you know, strategies as that original hardware out-of-order processor did, just in software at a coarser granularity. And then we're going to be able to build libraries on top of that did all the same things that, you know, we used to get out of our original, you know, single-threaded CPU. And it's just going to happen at a coarser granularity. So the analogy you should have in your head is effectively, you know, what used to be instructions and registers in your old, you know, single-threaded out-of-order processor, right, is now going to be at the coarser granularity of what we're going to call tasks, which are going to be, you know, sort of chunks of compute, right, and regions, which are going to be chunks of data. And I'll talk about what those things are. And, you know, just, you know, this is a sort of a slide, you know, very briefly to show you all the different ways that, you know, effectively software out-of-order processors look very similar to how hardware out-of-order processors work. They're just operating at a coarser granularity, but they're doing all the same things that you used to do in your old hardware out-of-order processor. Okay, so let me talk about how Legion and Legate fit into this design strategy, and then this will sort of outline what happens in the rest of this talk. So Legion is our implementation of this software out of order runtime. And it's going to be the first part of this talk. I'm going to talk about sort of the implementation of, or both the design of the API for Legion, as well as the implementation of the runtime system and how it works sort of at a high level. There are a bunch of traditional people who write directly to Legion at a bunch of the national labs here in the US. You can think of those as people that are like, willing to write assembly code. They're much more ready to talk directly to this runtime system and use it directly and run on lots of different scales of machines. But the second part of this talk is going to be about Legate. And in particular, we're going to talk about Legate NumPy, which is one of the libraries that we built on top of Legion to sort of describe how you can actually build these sort of composable libraries on top of our software out of processor. There's also Legate Core, which I'll sort of allude to a little bit as part of the Legate NumPy section, which is sort of our common execution API and data model for Legate libraries. I'll also talk about, at the very end, briefly some upcoming Legate libraries we're working on in addition to NumPy. And in particular, Legate NumPy has three parts. There's a NumPy translator, which is going to translate down to our API. There's a bunch of fast kernel tasks that run on CPUs and GPUs, and there's going to be a mapper that's going to help us get portability across the different scales of machines that we care about. And this is really designed at more of these HPC productivity users and data scientists. There's people who actually need HPHPC and not just HPC, right? They actually care about that high productivity part. It's actually very important to them. I'll talk about these upcoming Legate libraries a little bit at the end. Okay, so let me talk a little bit about how Legion works in the programming model and how the runtime is implemented. So any Legion program effectively is broken into two parts. There's a Legion program, which is going to be sort of a machine-independent specification of your program. When I say machine-independent specification, I'm going to dive into what that is, but effectively, it's going to be a kind of code that is portable across lots of different scales of machines, as well as older and newer machines as well. Importantly, this is going to define your application correctness. It's effectively going to how you're going to lay out your implementation of your application, but in a machine-independent way. And it's going to be based on sequential semantics, which is very important, right? We have to maintain that sort of illusion of a sequential program that you would get from like that sequential, processor that we alluded to earlier. And the important thing that Legion is going to do is going to do some program analysis to actually like build complex data flow graphs and infer implicit parallelism from these sequential semantics. And of course, the other part of this problem is like once you've written your machine-independent application, you've done dependence analysis and stuff like that, you've got to say how this graph gets mapped onto real hardware, right? And so we have a Legion mapping API, which is going to be a callback API, which is going to handle all of the decisions about placing tasks and placing data like the regions inside of different memories and stuff inside of your machine. So effectively, once this graph is going to be very, independent from your machine, and you need to say how that graph is going to be mapped onto that machine. And Legion will never make any heuristics. It has no heuristics inside of it for mapping it. We expose all of those decisions through the mapping API, so that mappers can actually make these decisions, dynamically on the fly, and it'll only impact the performance of your code. It'll never actually break the correctness of your code. Okay, so let's actually break down what these different parts are, the Legion program and the Legion mapper, and actually look at how they work from the user perspective, as well as how they're implemented inside the runtime. So these Legion programs are effectively going to be composed of two things. One is going to be describing data, and then it's going to be describing compute. So how do we describe data in Legion? Well, we're going to describe it with an abstraction that we call logical regions. And we're going to describe computations with tasks that are going to name their logical regions that they're going to access as part of their computations. So you can think of this, importantly as defining this machine-independent specification in two ways, right? Logical regions are going to decouple our specification of what data we're going to access from how it's going to be, placed in the memory hierarchy. And tasks are going to decouple our specification of what computations we're going to run from what processors they're going to run on. And this is what gives us our machine-independent specification. So, now most people usually at this point ask me, isn't this how all other task-based runtime systems do it, right? Don't they all just name tasks with their, subsets of data that they're going to access and so forth? And so I want to highlight a very important way that Legion is going to actually be very different than a lot of these other runtimes that you've probably heard of. So if you look at a bunch of task-based runtimes out there today, like Dask or Ray or Spark or so forth, right? They all sort of do what I call name-based dependence analysis, right? In Legion, we're actually going to do something very different. But let me just clarify what name-based dependence analysis is first. So if you have these tasks running along, and maybe you've chopped up like some large data frame over here on the right, has some rows and some columns, you've cut the rows and cut the columns in different ways. Your tasks are running along, and they say I want some chunk of data from those rows and columns from how I've partitioned up my data frame, right? And the runtime sort of says, okay, I can see that like T3 wants the same chunk that T1 wanted, and therefore I can infer a dependence between T1 because they're using the same chunk of data. But if I want to change to a new partition of this data, right, I effectively have to make a new set of features, a new set of names to describe that new partitioning. And I have to do like, sort of an all-to-all sort of swizzle exchange of that data and make, new sets of chunks or new sets of names for this partitioning of this data. And then I can go back to doing my name-based dependence analysis. And then if I want to switch back, I again have to like, insert another all-to-all swizzle exchange. Right, and this is really unfortunate because your users then have to, insert synchronization or data movement to maintain coherence between these different partitions. It also multiplies your memory usage, right? Because whenever you're switching from one partition to another, you're actually, using twice as much memory as you probably actually need. And finally, it really destroys that ability to compose libraries, right? You effectively punch it up to the user, the problem of data coherence. And you've also made it impossible for the runtime to sort of find task parallelism across those all-to-all swizzle exchange boundaries. Those are effectively like big barriers inside of your application. So Legion is going to do something different. Our regions are actually going to allow you to name, completely arbitrary subsets of data. So when you have, two tasks that are naming different subsets of regions, right? Effectively, they can go along and name, completely arbitrary regions, which define, arbitrary subsets of this data frame. And, you're just, naming what the set of data that you want to access. And when you want to do dependence analysis for a task, like let's say we want to do a dependence analysis for T6 to see what it depends on, we actually formulate this as a graphics problem. So you effectively like, draw a bounding box for the subsets of data that you want your task to look at, and you look backwards in time through all the rows and columns that region wants to access and see what you intersect with, right? Hopefully this is reminding you a lot of like a ray tracing problem. It's because that's effectively how we implement it. So we effectively render data for each task by looking backwards in time to see what it intersects with. And we actually do this, with very standard graphics techniques. Like we have big distributed bounding volume hierarchies for all of our regions to help us do these intersection tests fast and efficiently, even in distributed systems. And the one difference with graphics, I've made this kind of look 2D because it sort of gives you the graphics intuition. But of course, like we actually support ND dimensional lookups backward in time. And I'll just talk about how that works with regions here in just a minute. Okay. So let me give you an example of like using logical regions in practice and what they actually mean, so you can see why why it's valuable to have this sort of arbitrary subsets of data and how we can actually describe those with regions. Let's say we have a graph here that's going to represent a circuit simulation that we're going to run. So we're going to like have some nodes represent circuit components and wires represented by edges in this graph, right? A logical region effectively is a table that allows you to describe these different properties. So you can have a table for the nodes, and you'll have fields for each of the different properties on each node that you want to store. Right, so we call this an index space. It can be up to ND dimensions, right? In this case, it's probably just 1D, but if you want to have like an ND array, you can have that as well. We also have field spaces to describe those fields. And what we're going to do is we're actually use these logical regions to create subregions, which actually describe subsets of these nodes that we want to access. Let's say I represent all the nodes in this graph with this top level logical region here, N. Just think of that as representing the table that we saw before. And maybe I have some partitioning of this graph. Maybe I call like parmenas, it chops up in my graph into some pieces for me. Right, and now I want to describe the subsets of nodes, that are either private or shared. The blue ones are the private ones, the ones that don't have any edges that cross between different circuit pieces, and the red ones are the shared ones. So Legion actually gives you the ability to make partitions, describe the subsets of private and shared. And then you can recursively decompose further down into further subregions. So you can even define like the set of private nodes for each of the different pieces. So you can make a partition that describes each of the private pieces for each of those, circuit chunks that you want to describe. We can do the same thing with the shared nodes. We have a partition for each of the circuit pieces for its shared nodes. And we also support multiple partitions in Legion. So you can even have like multiple partitions describe like your ghost zones, right? Like effectively one edge hop away, from your shared nodes and finding that transit closure there. Right, and so Legion allows you to describe all these arbitrary subsets of data that you might want to capture as part of your program. And then you're going to launch tasks that name each of these different pieces. Importantly, this data structure here is actually a real thing that the runtime actually maintains, and something that programmers think about a lot in Legion. Effectively, it's what we call a region tree. It describes subsets of or subregions and the relationships to each other. Right, so we know things about locality. Right, things that are in a subregion are often going to be located together for compute purposes. We can see independence. So two subregions, like in a disjoint partition, like the private one, are known to be disjoint. We can even prove things like S1 and P1 are independent from each other because they share a common ancestor partition, which is disjoint. And again, this is actually helps feed into the bounding volume hierarchy. Like knowing this independence actually is how we construct things like bounding volume hierarchies for our graphics intersection tests. We also know subregion stuff, which gives us stuff like aliasing, right? So if you can prove that one subregion is an ancestor of another, right? That implies that there's some aliasing there because of the subregion relationship. And you also get aliasing, in cases where like, in the ghost zones, we even have an alias partition there that, says that all the partitions could, or all the subregions in that partition could be aliased with each other, right? So they can possibly overlap there. And you can also possibly overlap with things in, adjacent partitions, right? So these are cases where we actually have to do proper intersection tests in our bounding volume hierarchy for our graphics intersection tests. So I talked a lot about regions. Let me describe about how tasks work. So every Legion program is a sequential program, as I mentioned before. And so the way that manifests itself is that Legion programs are effectively a tree of tasks, just like you would have like a tree of function calls and sort of a sequential program. We have trees of tasks. And so every task has to name the sets of subregions that it's going to access when it runs, right? So effectively, our top level task might be running along and taking off subtasks that are naming different chunks in our or different subregions inside of our region tree that it wants to access for doing its compute. Right, and this is just a sequential program, right? It looks like a sequential program. It has different subsets of data that's going to access. Those are like sort of your analogy to your register arguments. And we call these things your region requirements, right? These are the sets of regions this task needs to actually run, right? And it consists of a logical region that the subset of data you want to access, the fields, effectively the columns in the table for the logical region you want to access. And finally, it's describing, you also name your privileges that you want to access that region with, right? Whether it's read only, rewrite, or reduce. We actually support like user specified reductions as well. And of course, this program, as it's running along, is getting fed into Legion, and Legion is doing some dependence analysis to build this sort of dynamic data flow graph to represent the dependencies between all these different tasks. Now, importantly, just like a good hardware out of a processor works, right? We're effectively doing all this like asynchronously with a pipeline of execution, right? So as your program is running along, kicking off tasks, right? We're filling in dependencies. So there's effectively a construction wavefront where we're building the dependence graph for all of your tasks as they're running along. There's an analysis wavefront that's filling in those dependencies. There's an execution wavefront where we're actually executing tasks and actually doing their compute on CPUs and GPUs and stuff. The distance between these two things is effectively your data movement window. That's how long you have to move data, and you can overlap compute and computation that way. And finally, there's a destruction wavefront, right? Like we effectively have a fixed set of a window, a sliding window, sort of like your reorder buffer that says like how many tasks you can have in flight at a time. And we don't allow it to get too big because that would consume too much memory. So you have a destruction wavefront cleaning up tasks, which will then allow your program to run further into the future and make more tasks. And so this is neither eager nor lazy execution. We call this deferred execution. It's different than I get this question all the time. How is this different than things like TensorFlow and PyTorch, which do lazy evaluation? And the answer is here we're doing all this dynamic on the fly, and we're not waiting for things to finish or for like loops to be completely unrolled before we start analyzing them. We're just running ahead and doing the analysis in real time. So we're constructing dependence graphs on the fly, and we can handle things like dynamic control flow and stuff like that as a result, right? We're not bound by a lot of the restrictions that you get in some of those lazy evaluation DL libraries that you see in lots of other contexts. Okay, and when Legion actually goes to prove interference tests, like I was mentioning earlier with the graphics tests, right? The first dimension that we do it on is the logical regions, because that's actually one of the faster ways of doing it. But that's effectively testing for interference on that index space. But you can also prove it in other ways. So for example, if you can prove that two tasks are using non-overlapping fields, right, then you can also prove that two tasks could potentially run in parallel. So you can infer implicit parallelism on your fields as well. And finally, you can do it on privileges, right? If you have overlapping sets of rows and columns, then you can still prove that two things are read-only and can potentially run in parallel. So people then ask, if you're doing all this dynamic dependence analysis, how much does it cost? Well, it really depends a lot on your application, but let me give you a feel for how it's advanced over the years. Dynamic dependence, well, I'm actually going to advertise why it's important, right? Dynamic dependence analysis is actually the thing that gets us, all the important properties of Legion, right? It gives us performance portability, resilience, interoperability, programmability. They all come from the fact that we can sort of react to your program and your data and your machine on the fly. And by doing a dynamic dependence analysis, we really are very flexible in the kinds of programs that we can handle. Back when we first started writing Legion in 2011, your task had to be about 10 milliseconds worth of compute, right, in order to make it so that you wouldn't be dominated by runtime analysis overhead. Right, in 2013, that actually came down to about 5 milliseconds. And today, we've gotten it even further down. It's now down around about 1 millisecond, maybe about 500 microseconds for experts that are willing to do some more tuning. And we also have a facility for tracing. Effectively, it's like a trace cache, where if you have repeatedly executed chunks of tasks, we'll recognize that and sort of replay our analysis. And that gets really efficient because then you're not doing that dynamic dependence analysis all the time. We've actually cached your graph and are replaying it. And so then you can handle like chunks of tasks that are like, down around 20 microseconds worth of compute, which is very, very, very tiny. In fact, very tiny enough that most people wouldn't even recognize it at that point. Another thing I'll mention about Legion here is that Legion actually supports running different tasks with different languages. So we actually allow you to mix and match languages inside of your tasks. So you can actually have a program consisting of like many different languages, each of which are using different tasks. And because we're passing data back and forth with regions between these tasks, right? That gives us sort of a common interface for mixing and matching these languages in the same program. So we support C, C++, Python, Lua, Terra, Regent, Fortran, and CUDA. So you can put pretty much any of those things. And I guess I should now add LLVM. So you can even have tasks that are written directly in LLVM IR. And you can sort of mix and match those things inside of your program, which is really a valuable feature. In fact, it's going to be very important for Legate. Yeah, so we can mix and match those things. And importantly, one of the things you can do, which is really cool with Legion, is you can even register like multiple different variants of the same task, which are effectively functionally equivalent functions to run for each of those different tasks. And you can sort of let your mapper pick like the right one. So, for example, you might choose to map a task, to a CPU in one case and run it with like normal C++ code. But you might also register a variant, for running on a GPU. So if you've got a GPU available and it's, not too busy, you can schedule that task on the GPU and pick the GPU variant and run with CUDA and so forth. Okay, so that's effectively how you define Legion programs, right? And you remember there's another thing called the Legion mapper, right? The mapper is the thing that actually decides how you're going to map this program onto a particular piece of hardware, right? So the mapping interface controls, among other things, where tasks run and where regions are actually going to be placed in the memory hierarchy, right? So if you've got some machine with some processors and some memory hierarchy, you've got your task graph that the runtime has computed, to figure out all these dependencies. Effectively, your mapper is going to say where those tasks can get placed. You might put some on the CPUs, some on the GPUs, and you've got your region tree. You've got to say where each of those subregions are going to have instances created. Whether they're in different memories throughout the system. And importantly, the mapper gets these callbacks dynamically, right? So the mapper is actually computing the mapping on the fly, right? This isn't a static specification. You effectively, can alter your mapping on the fly as a function of what your machine is doing or what data you're seeing, right? If you're data, if you're loading different data, and your program reacts differently to data that you're loading, you can even change your mapping decisions on the fly to react to that. And the key property of mapping is that we decouple, the correctness of your code from the performance. So no matter where you choose to place your tasks and where you choose to place your data, Legion always inserts the right copies and synchronization necessary to actually make it so that your program executes consistently with the sequential semantics of the original machine-independent specification. You cannot break your correctness of your code. Yes.
A question from the chat.
Sure.
Does it support F to Pi bound Fortran code?
F to Pi. So I'm assuming that translates Fortran to Python. And assuming it's normal Python program, then yes, we would support that. Like effectively, we don't care what you do inside of your tasks, right? It's effectively just generic implementations of the languages. Hopefully that answers the question.
Perfect.
Sure. So let me give you a brief example of why Legion is so powerful. And you're going to see there's nothing actually magic about Legion itself, right? There's like effectively, because Legion has no heuristics and no real program transformations, it's just doing a standard dependence analysis. You might be wondering, like, what is actually the thing that's actually important here? So an example of this is, we wrote a giant, combustion simulation called S3D. We translated it from, some MPI plus Fortran code into Legion C++. And effectively, we actually ran on a bunch of supercomputers, including, porting it from Titan to Keelan, and also porting to Piznate, which actually you guys probably know more about than I do. It actually takes very little time to port using Legion, because effectively we just have to write new mappers. But the important takeaway that I want you to get from this is, this is a comparison of, the Legion throughput running on, up to 8,000 GPUs, comparing Legion to a very tuned code using MPI plus OpenACC, where a bunch of NVIDIA dev techs actually worked on the MPI plus OpenACC code for a number of months. It's anywhere from like 1.75x to like 2.85x faster than the MPI plus OpenACC code. And there's no real magic for why that's the case. In fact, the reason that that's the case is really the complexity of the dependence graph that this application actually generates. Right? It's actually incredibly complicated. And humans are really, really bad at scheduling this kind of complexity, right? We're actually, this is like, this is the reason that hardware auto processors were successful too, is that they could find ILP that, humans would never want to write and were actually too hard for the compiler to prove statically, right? Effectively, you don't want to place all those MPI sends and receives in just the right place for the right machine, and it kind of destroys the structure of your code to sort of reorder things to describe the best possible performance ordering of compute and overlapping of computation communication. It's much better if you specify it in some order, sort of a program order that makes sense to you, and have the system sort of reorder things for you, to react to how the code is actually running on that machine. As applications and machine complexity increases, this performance gap continues to grow. There's not really anything magic behind it. It's really just, humans are just really bad at dealing with large amounts of complexity. And this is true both for HPC and data centers. So effectively, Legion is providing, support for these library developers that we talked about at the beginning of the talk, right? We effectively given them a data model that they can sort of offload a lot of the complexity for how they describe their data onto Legion. They don't have to worry about placing data in memory hierarchy, and they can create arbitrary partitions, describe arbitrary subsets of data, right? And they can also offload compute. They just describe their tasks. They don't have to worry about where they're running and so forth. And then they can worry about placing them with the mapper later without breaking fragments, right? It's not really and finally they get to maintain the sequential semantics, right? They don't have to worry about doing placing all the right sends and receives and putting in synchronization and copies and all those kinds of things. They just describe programs, with tasks and data they're going to use, and just say, punt that over to the runtime system and let it deal with it. So we're providing a pressure offload release for them. Okay, so I've described Legion, and I now want to talk about Legate NumPy and how it works on top of Legion, and how it sort of shows that you can actually build really effective libraries on top of this sort of abstraction of a sequential processor, even for running on large scale machines like supercomputers. So Legate NumPy is endeavoring to be a NumPy replacement for what we think of as transparent weak scaling. And really, when we say a NumPy replacement, what we mean is that you really only change one line of code, right? We want to change, you change that import statement from import NumPy as NP to import Legate.NumPy as NP, and that's all you've got to do. After that, your code should be able to run on pretty much everything from the GPU on your desktop to like a DGX station to DGX SuperPod to the Summit supercomputer, right? There should be no reason that you can't run the same code on your desktop as on the Summit supercomputer. And it really has to be this simple for a lot of reasons. One is that there are a lot of users out there today who need the compute power of like the DGX SuperPod or the Summit supercomputer, but they don't have the programming skill to target it, right? They're not going to write MPI plus CUDA, right? They really will only be able to work with like Python level libraries and sequential code, but they really do need that compute. There's lots of really compute heavy problems out there today and lots of big data analytics that really need this kind of solution. And second, the reason to have a drop-in replacement without any code changes is that there's lots of software that's built on top of NumPy, right? Remember that stack of libraries that I showed you earlier. And if you require code changes, then all those libraries stop working, right? So you really need to provide a drop-in replacement. So here's a really simple example of Legate NumPy working in practice. So here's a little program. This is a Jacobi solver, right? You just build a matrix and fill it with some random values and start trying to do solves on it. It's sort of an iterative solver. Right, and we're effectively weak scaling this particular program, right? So you start with like a 1.5 gigabyte matrix over here on the left, and you go over to like a 400 gigabyte matrix on the right. And so Legate NumPy is the green and red lines going out to like 256 GPUs all the way at the right, or 64 20-core CPUs in the case of the red line going all the way to the right. And you can see the difference between standard NumPy as well as CuPy. Note this is a log plot. Just because of the difference in scales and performance here between like CPUs and GPUs and so forth. And so, yeah, you can see the different scales of machines that we're running on. And so this is really powerful, right? You can now program like an actual supercomputer, with 32 nodes, with 256 GPUs, right, with just standard NumPy. And that's an incredibly powerful thing for a lot of people who really need access to these kinds of things. So how does Legate NumPy actually work by targeting Legion? Let me give you a feel for how it actually is implemented in practice. So you've got your NumPy program, right? And it's running along, doing NumPy API calls. And what it does, when it calls into Legate NumPy, what that does is going to turn around and launch some tasks to actually do the computation for that particular NumPy operation. And, as your program runs along, each of these API calls is going to turn around and launch off more tasks to be performed for each one of those computations, right? And when we actually go to run those things, right, we have fast implementations of those tasks, right, written in C++ and CUDA and OpenMP, right? This is where the value of Legion supporting multiple different tasks in the same program is useful, right? So you have your top level task, which is written in Python, running this NumPy program, and then you've got tasks that are farther down in your task tree, running C++ and CUDA and OpenMP and all sorts of non-Python libraries or non-Python languages. And then we've got a mapper, the Legate NumPy mapper, which is deciding how to map these tasks onto various different processors based on the understanding that it knows it's mapping NumPy code. Right, and all that gets fed into Legion, and that's how we get our execution onto lots of different scales and kinds of machines. So I talked about the tasks. Let me describe how data works also in Legate NumPy. Right, so Legate NumPy effectively maps your ND arrays in your NumPy program into the Legion logical region data model. Right, and I'll talk a little bit about how that works in a minute. Right, and Legion can then do the dependence analysis, right, that we were talking about before, right, because we know which regions each of these tasks are using, so we can figure out where dependencies are. Legate mapper comes along, says what runs on CPUs and GPUs. Legion inserts all the copies and synchronization between those tasks. And you'll notice now that we've got sort of an out of order execution of this program, right? We ran the program in one order, but we actually got tasks running out of order, but still consistent with the original sequential semantics of our original program. And so that's sort of,
a couple of questions
Sure.
in the chat for you. So first one, when you mention standard NumPy, does this refer to a NumPy installation linked against a BLAS implementation like MKL or the pure Python implementation?
So I'm talking, that was actually, let's see if we can actually go back to this talk, to the slide up here. So this is actually canonical NumPy with no open BLAS or MKL. I'm going to show an example of some performance a little bit later in the talk that actually is against Intel's NumPy with MKL support for multiple threads. So we'll see that a little bit later in the talk. Yeah.
Perfect. And then another question: how does Legate NumPy offload loops, and what is the overhead while using loops? Right.
So, I mean, with all good NumPy code, it's much better if you push the looping into API calls. So if you look at this little program here, right, this subtraction is actually doing a loop over all the points in each of these two matrices. Hopefully can you guys see my cursor?
Yes.
Yes. So this subtraction here is actually an implicit loop over all the elements in each of these matrices. So it's much better to write code like that. But loops like this, where you're looping over big NumPy statements, which are doing lots of things, are fine. If you do a loop over all the elements in A, we're not going to do anything magic to help you, right? That'll actually not perform very well at all. So we're kind of, we kind of hope that people sort of follow the NumPy convention, that you push as much looping over the element-wise, operations and stuff into the syntax of NumPy and let that looping happen inside of NumPy. And if it does, then we can do good things for you. I mean, we're not going to do anything to stop you from looping over the elements of A. We might give you a performance warning, but we can't stop you from doing that. So it's much better to follow the NumPy conventions of pushing, the element-wise looping into NumPy itself.
Makes perfect sense.
Yep.
That's all our questions right now.
Cool. Okay, let me jump back to where we were here. Yeah. So effectively, this is how we can leverage Legion to actually take advantage of, or have Legate NumPy take advantage of the features of Legion to get good performance for actual NumPy codes running on heterogeneous hardware. Okay, let me talk a little bit more about how data actually works inside of Legate NumPy, because I think it's actually very instructive for how Legion actually provides a lot of the semantics that you really want when you're a library developer, like someone building Legate NumPy, right? So each of your ND arrays are going to map to a field of a Legion logical region. Different logical regions will make different logical regions for each of the different shapes, and we'll have different fields for each of the different arrays, so we can dynamically allocate types on them, and then we'll recycle fields when they're garbage collected in Python. So let's look at this Jacobi solver example here, and let me show you how this works in the Legate NumPy backend, right? So when we hit the statement here, the first statement, we're making the A matrix. So we'll actually make a logical region in Legion, which has an index space that's n by n. And what we'll do is we'll allocate a field in that logical region that corresponds to I sub aj, and that'll store all the data, or be the backing representation of all the data. I should say it doesn't store; it represents all the data for the A matrix. Right? I give this B vector. I say, okay, I don't have a region for that shape yet, so I'll make a region with index space n, and then I'll start allocating a field for B sub I. And I go down to the program, and each one of these new statements corresponds to making a new vector. I've already got a region with the right index space, so I can make a new field in that particular region. I can do this all the way down. When I get to R, right, that's another one in the n by n region. And then as I iterate my loop, right, I fill in entries for each of the different iterations of that X vector that get made. right? So we can effectively use the ability to create logical regions on the fly and allocate fields on the fly in Legion to handle, the dynamic creation of representations of data for each of the different arrays that need to get made in Legate. This is probably the coolest part, and probably one of my favorite, is NumPy supports this really interesting syntax where you can actually make views onto arrays, right? So you can actually make you make a grid here that's going to represent like a simulation. This is actually going to be like a sort of a stencil computation written in NumPy. So you can have this ability to create views onto arrays, which are effectively a view is a subarray. But if you mutate data in the subview, right, it has to be reflected in the parent array. And similarly, if you mutate data in the parent array, it has to be reflected in the subview, right? And so NumPy supports this kind of cool like aliasing property where you can mutate data in one place and have it show up in another, right? These are all just views onto different subsets of data, right? And so Legion is actually going to support this very naturally with our partitions. So we're going to make this, when we make this grid array here, right? We're going to allocate a logical region for the grid. It'll be n+2 by n+2, right? And when we get down to the statement here, which is actually going to make a view, it's going to make this center view onto this grid array, right? Legate NumPy actually creates a partition to describe that subview. So we call these indexing partitions. Right, and as far as Legion is concerned, it's just a normal partition, but Legate NumPy calls it an indexing partition. And so it describes a single subregion that describes the subset of points that correspond to that center view of that grid array. Right, and each one of these different views that get made correspond to new partitions. Right, and so we can effectively just create dynamic partitions on the fly using Legion's ability to make partitions on the fly to represent the subregions that are going to correspond to the different views that get made. Right, and Legion has the same semantics that NumPy does, which is that these subregions are naturally aliased with their parent regions, right, that represent the original arrays. So if you change something in one of them, it'll show up in the other ones. We also use Legion support, to create, partitions and stuff to make, what we call natural partitions, which are the partitions that describe, the chunks of each of these views that we're going to use on like, however many GPUs or however many CPUs we're targeting for different computations, right? So I can effectively make partitions describe the partitioning of each of these arrays, for however many processors I'm going to be running on. We call those the natural partitions. And importantly, Legate NumPy can just launch tasks using any of these subregions, and Legion maintains the coherence of that data, right? You don't have to worry about issuing copies or synchronization to maintain coherence between these different views, right? You just offload all those problems onto Legion and let it deal with it. So finally, I want to talk about the Legate NumPy mapper and how we actually make policy decisions to actually handle like the mapping of NumPy API calls. So like, let's say we've got a GemV computation here with this dot statement. So we've got a matrix A times a vector X produces a new vector Y, right? And we're gonna map that onto 4 GPUs. So for the first question, the Legate NumPy answers is, do we offload this to Legion or not? So if we don't, if these inputs are actually really tiny things, we actually probably will just call them in line and do standard NumPy to execute them. Like if it's a little 2x2 array or 2x2 matrix, it's not worth offloading Legion, right? So you want, a big chunk of a bigger array to actually offload this computation. Right, and so the first thing we do is we look at each of these inputs to this and outputs to this computation and say, which one is going to be what we call our key array argument. And the key array is going to be the one that has the most data in it, because it's the one that we want to use with its natural partition, so that we don't have to move too much data, right? We want to move as little amount of data as possible. So given that we have natural partitions of X, Y, and A corresponding to different subregions for each of these GPUs, we look at each of the arguments and we say, okay, A is obviously the biggest one, so we're going to use A as the natural or as the key array argument. And we're going to use its partition to define, how we're going to map this computation. So we say we keep A in place, and then we say, okay, let's actually make new partitions for the subsets of X and Y that we actually need to do this GemV computation. So we make new partitions if they hadn't already been made, describe, the subsets of X and Y we need for each of the computations, right? And then we can launch tasks that are actually going to use those to do the GemV computation on each of the GPUs. Next, we decide where we run our tasks, so we can place our tasks in different places. Importantly, we place them in such a way that we actually take advantage of NVLink. So we have to do the reduction after this initial GemV computation. We know that we've placed the summation part in such a way that we can do this over NVLink. And so the NumPy mapper is smart enough to handle those kinds of decisions. Right. So we have to place data in such a way to take advantage of that also. And importantly, this is Legate NumPy's ability to take advantage of Legion's mapping interface and to be able to specify these things independent of how we want to handle correctness, as well as giving us the ability to change these decisions on the fly. If say we move to a new machine, or if we detect the new data is coming in of different sizes and stuff, we can change mappings and so forth. So we get to sort of take advantage of Legate or of Legion's ability to give us this separate interface to change mappings without having to worry about breaking the correctness of our original code. Okay, and I'm actually running out of time, so I'm actually going to skip this slide. Happy to take questions about control application, which is our most recent PLDI paper, or sorry, our most recent PPOP paper later, or offline, but I'm going to skip that here because I don't have too much time left, I don't think. Okay, so let me give you a little bit of a performance comparison for, comparing Legate NumPy against a bunch of other versions of NumPy drop-in replacements or near drop-in replacements. So we're going to compare against standard NumPy, single nodes, single threaded. I also mentioned earlier that we'll have a comparison against Intel Py. So this is Intel Python with MKL, where you actually get some multi-threaded acceleration, but it's still not able to go off a single node. Right, we have two versions of Legate. We'll have CPU-only Legate, as well as Legate with CPUs and GPUs. And then finally, we're going to have two other lines for comparing against Dask, which is a very popular Python library used for parallel and distributed computing that's used by the NVIDIA Rapids team. And they have an array, or what they call a library built on top of Dask, which is called Dask.array. It's very, very similar to NumPy. It's almost a NumPy drop-in, except it has some API changes. It actually requires you to do things like specifying how you're going to chop up the chunks of your array for various different machines. So you might have to, for each of your different arrays, so you can either do that explicitly, you can say like, chop this n by n array into c by c chunks. You can also pass in this like auto string to allow Dask to try to guess a good chunk size for you. So we'll have two lines on the Dask for Dask. One is going to be the auto one, which is where we passed in the auto string to allow Dask to pick chunking factor, which is effectively what Legate is doing implicitly for you. And then we'll also have a tune line where I've actually gone through and run a brute force auto tuner to try and like tune all of these programs to find the best possible chunking factor for every array for various different machines, so you can get a feel for like what the speed of light, peak performance could be from Dask program if you actually tune it very well. You'll note, pay attention that all these plots are going to be log, just because of the varying scales of performance that you're going to find from each of these different systems. All of these were run on a cluster of DGX 1V nodes with 8 GPUs per node and InfiniBand. And we're going to be plotting weak scaling here. So problem size is going to grow proportionally with the number of sockets that we're going to be running on, either CPUs or 24 CPUs or V100 GPUs. And what you're looking for are higher and flatter lines is better, right? So we're plotting throughput. So higher is better and flatter for weak scaling. So just keep that in mind. Okay. So here's that Jacobi program that I showed you before, just a very basic, simple example here to give you a feel for how for what that looks like here with some other lines on it. So you can see various different performance plots here. You can actually see that Legate NumPy is actually scaling pretty well, both with CPUs and GPUs. Dask is doing okay, but it suffers a little bit because it has a sequential scheduler, which prevents it from scaling quite as well. And that sort of, causes its scalability to tail off as it scales up. And yeah, you can see Legate NumPy is actually pretty comparable to CuPy on a single GPU, but it's of course able to go out to many more GPUs. Comparing against Dask, we're about doing about 10x faster CPU to CPU. That's really the apples to apples comparison, because at the time that I ran these experiments, Dask didn't have GPU support. So that's sort of a fair comparison. This is a less fair comparison, so take it with a grain of salt. But Legate NumPy is about 100x faster comparing CPUs to GPUs. So Dask does have GPU support now, but I haven't had a chance to actually benchmark it yet to see how well it does. And effectively, its benchmark is effectively replacing its tasks with CuPy tasks. So it's not like pure Dask code. And you can see there's different interconnect technologies here. It's always useful to keep in mind, effectively you're doing NVLink up to 4 GPUs, then you've got some PCIe communication between 8 GPUs, and then InfiniBand going across the other ones. Okay, here's another benchmark that we did. This one is sort of a sanity test to see that we can weak scale perfectly for something that has no communication. So Black Shells should be a perfectly weak scaling application because there's no communication between the options pricing. Right, and Dask actually starts out a little faster than Legate. They actually do some task fusion to actually fuse their tasks together. So like on one socket and up to like 2 sockets to 4 sockets, they're actually doing some fusion there. But then again, they tail off, right? Because they actually have to trade off some of that task granularity to actually scale out. And so they don't scale nearly quite as well as the Legate NumPy implementation on CPUs. Here's another example of like sort of a very challenging communication pattern, right? So we're doing logistic regression. This is full gradient descent logistic regression instead of like stochastic gradient descent. So what that means is you've got like all of your data in memory at all times, and you're doing a full reduction down to like, in this case, 32 weights, and that then has to be broadcast back out to all of your GPUs, right? So it's a really, really hairy sort of communication problem that can present scalability bottlenecks. It's very, very unusually shaped geometries to compute those weights and then to broadcast them back out. Right, and so you can see Legate NumPy is actually scaling very well. The smaller task granularity for GPUs causes us to tail off a little bit at the end there, but CPUs are doing very well. And you can see a case here where actually the fact that DAS actually makes you pick chunk sizes is actually mattering a lot, right? Like you can actually see a huge difference between the tuned and the auto cases. It's almost like an order of magnitude, right? Whereas Legate NumPy doesn't ask you to pick those chunks at all, right? Like effectively our mapper is intelligent enough to help pick those chunk sizes for partitions for you. And you just don't have to worry about it, right? So we're effectively preventing you from even having to think about that kind of problem. And here's our effectively our stencil computation from before. We're actually building those very interesting array views to actually do these computations. You can see Legate NumPy is actually getting perfectly scaling here, as you would expect, because it's really just nearest neighbors computation. But of course, like Legate is offline with Legion, which is figuring out that there's nearest neighbors computation. There's nothing explicit that tells that Legate NumPy does to say that it's explicit nearest neighbors computation. And you'll notice there are no DAS lines in this plot, right? Effectively, like DAS doesn't even support these array view syntaxes, right? You can't even run the program. DAS will actually give you an error saying that they don't support that, right? And because it's a really hard problem, right? You actually have to do that really nasty dependence analysis on really weird subsets of data, right? And Legion just offloads that, or Legate NumPy offloads that to Legion, which does it with its cool graphics algorithms. Whereas like Dask, is still stuck in that name-based dependence analysis world where they can't even handle programs like this. And of course, here's one of my favorite ones, this preconditioned CG solver, just because preconditioned CG solvers are always very painful to implement, usually if you try to write them in like MPI plus CUDA. And here you can just express them in NumPy very simply. They're really kind of simple. And we're getting pretty decent scaling. We have a little bit of work to do some more on the GPU one where the tasks are shrinking very quickly, but the CPU scaling is actually very good. We're pretty happy with that. So, one of the important things that I think you should take away from this talk, I talked a lot about Legate NumPy and how it works on top of Legion. But the same principle that Legate NumPy employs, just offloading these tasks to Legion and letting it, find dependencies and reorder things, applies across library boundaries also, right? So libraries in Legate don't have to be knowledgeable about each other, right? You can effectively have like a program that consists of mixing things like NumPy and Pandas and scikit-learn all in the same program. And all they have to do is kick off their programs in sequential order, launch their tasks, launch their tasks in sequential order, describe their regions. Legion will figure out the data dependencies between those computations because they're all using regions. They can make their own partitions, it doesn't matter, right? And Legion can then reorder things, and you get and put in all your copies and your sends and receives to remote nodes, and you effectively get something that looks like a standard Python program executing like a very tuned HPC program. And this is sort of what we're really excited about, is this composability of these various different libraries, right? The ability to make them play nicely together means that people can actually build an ecosystem that still looks like standard NumPy or standard Python, but executes much more like HPC. And they don't have to, and even those library developers that we talked about at the beginning, don't have to worry about knowing about how their library is being used or how it's interacting with other libraries, right? We're removing that requirement for them to understand the interactions between different libraries for them. So this is sort of what Legate NumPy what the Legate Legion ecosystem looks like today. You can actually get access to the early access version of Legate NumPy today, and I'll give you a link for that at the end of this talk. We've also been working on Legate Pandas. You can't quite see that one yet, although stay tuned. You're hopefully going to get access to it very, very shortly. So be looking for that. There's another programming system on top of Legion that's actually being built, by CMU and Facebook and Los Alamos called FlexFlow, which is actually, an implementation of like the Keras API on top of Legion for doing like deep learning training and stuff like that. It actually, it shares a lot of the same properties of NumPy, and so it actually will operate with Legate NumPy if you get the early access release of that. So you can go check that one out. That one is actually open source, and so you can go test that out. And we also have plans to look at other future Legate libraries, scikit-learn, PyTorch, and so forth. Are there any other libraries that you guys are interested in? We'd be interested in hearing about what you think are interesting Python libraries to target. So anything that you think is interesting, we're open to suggestions. This is sort of what this is sort of our ideal Legate ecosystem. So with that, I'm going to open things up to questions. Here's places where you can get some additional information about various different systems. So there's a Legion website. Legion is open source. It's been open source, since day one. You can get it on GitLab or GitHub, either one. There's also the Legate Early Access Program. So you can download a copy of Legate. It's not quite open source yet, although, like I said, stay tuned. And hopefully it'll be coming open source somewhere in the near future. I can't tell you exactly when. And if you've got specific questions or comments, I'm always happy to hear them. So with that, let me take questions and hear what people have to say.
Thank you, Mike, for the lovely talk. When I was back doing my PhD, I remember reading about Legion and Legate from almost the start of it. So it's really interesting to see how it's evolved over time. And before we move to questions, our next SPCL Bcast talk will be on the 25th of March at 6 p.m. Zurich time. Gerhard Walling of Friedrich Alexander University will be here speaking.